So everyone, welcome to the last Coffee with Caleffi of 2025. We have kind of a cool topic here today. We actually had a question that came in that was a pre-submitted question that said, how do you quantify the tipping point where added system complexity no longer yields proportional energy savings? And I think that's kind of the thesis statement for this presentation, to discuss, what is that balance between simplicity and energy efficiency and the ability to troubleshoot and things like that. And we've got a great presenter for that I'll introduce him in a second. So if you want to go to the next slide, I'll cover a couple of the FAQs. If you're having issues with GoToMeeting, with GoToWebinar, usually the best case scenario is you just log out and log back in. But here are some of the other questions. If you want a copy of today's presentation, I actually added it as an attachment that's up in the top right in that materials. There's like a little paper clip with a document. You can get the PDF there, or we can send it to you in an email afterwards, and then we'll put this up on YouTube later today. Then depending on the next slide, depending on your jurisdiction, we will send you a certificate of attendance, and you can self-report that if you want to. So it's got all the information that they usually ask for there, and that will be sent to all the attendees after the webinar. Then on the next slide, Hydronics 36 is up. I'll put that in the chat as soon as we get started here, but 36 is all about zoning, and we've got the PDF up, and the actual physical copy is off at the printer now, so you should be getting those shortly. And then on the next slide, I'd like to introduce our presenter today. So Jake Fear is the owner of Simple Hydronics in Montana. I met him when he was a rival manufacturing rep when I worked at Shamrock Sales in Colorado, and he was at TM Sales. Really knowledgeable guy, wide skill set to cover the idea of the system all the way through the commissioning, and I think is a good example of the Montana contractor support system who just really has to figure it out. There's not going to be a factory person isn't going to land on a helicopter at a job in the middle of Montana every day. So he's has been to many systems to get them across the finish line and make sure that they're exactly what was bargained for from the design standpoint. So with that, I'll turn it over to Jake to roll through the rest of the slides and keep an eye on the questions. Thanks for joining, Jake.
Oh, absolutely. Thanks, Max.
Yep.
Generous introduction. I'm Jake. Like Max said, I own Simple Hydronics. We kind of specialize in a consulting, design, troubleshooting, fix your issues type model. Mostly based in Montana, but do some work elsewhere as well. So today, I'm going to get through our slides here. Bear with me as I figure out doing this virtually. Max approached me with a question similar to what he just said. What would be something good to talk about in the hydronic design area? And we came up with this idea of trying to find the balance of simplicity and performance in hydronic design, and not just in design, but in system install as well. Just so we're clear, what we're talking about here isn't what is wrong with systems, and it's certainly, I'm the last person who's going to tell you how to go do your jobs or how to design something and that what you do is wrong. The idea is really to present some concepts that I've utilized with success and that we can put into a basic system design that will get the simplicity and the performance that everybody's looking for, can hopefully perform in the future and keep systems running. Max, do you want to chime in on this one? I know you added this.
That one, sorry, I added that one late. So we've been featuring a charity or some sort of group every month. One of the things I just wanted to point out, this isn't a specific group to support, but I just pulled a couple of Bureau of Labor Statistics things. Great news. There are going to be a lot of jobs available in the HVAC market in the future. So a lot bigger projected growth than other industries. The bad news is we're going to lose a lot of the highly skilled, the way that ACA defines it is kind of within that population. The highly skilled master level contractor is somewhere in the 55-year-old range. So we're going to lose a lot of knowledge in the next 10 years in the industry. So this is something that probably most, if not all of you on the call are aware of in some capacity. My plug this month, I guess, is to find a trade school or whoever is teaching people like you in your area and donate a little bit of time or an old tool that would be helpful to put a system together, or your expertise somehow. I think that this will be a great career for a lot of people, but we're losing a lot of the people that know how to do it. So that's kind of my vague plug for December. Back to you, Jake.
Yeah, and in that line, even something as simple as if you have kids going to their what do my parents do, kind of job day at school. I did it last year for a first grade class with the complete expectation that nobody would have any clue what I do, or even I struggled to explain what I do to anybody. But I took a thermal imager in with me, and it turned out I had more questions than any other occupation who showed up for the entire month, just by talking about heating and taking a thermal camera with me and showing off how some things are hot, some things are cool, and how you can transfer heat. So some of these goofy little things just gets kids interested in what we do at a young age, and that can carry through to where we need a high level of involvement in our industry moving forward. Um, so agenda for today, we will work to get through all of this. I have a tendency to go on tangents. If any of you have sat through one of my in-person trainings, what's supposed to be 4 hours turns into 8. So I'm really going to try to keep this short and sweet and get through the information. If you guys have questions, please feed them into the chat or comments or anything else, and we'll try to address most of them at the end. If something comes up that Max thinks is pertinent at the time, he'll interrupt and we'll go from there. So I want to work through kind of the basics behind a simple philosophy, what we need to know, what the big things are that I think are the basis of any design. So knowing our loads, separating flows, pump away, minimize and lower our water temps, and then why simpler is better most, but not all the time, right? We also want to look at, is our system simple enough for the next contractor to figure out? Just because you understand what you did when we're piping or designing something doesn't mean in 5 years somebody's going to be able to come in and figure it out fairly quickly. I know we all like to think we're going to work on systems for the rest of that system's lifetime, but it's just not the case most of the time. And then future proofing, how do we account for the next generation of heat sources, regardless of what our personal feelings are on heat pumps or geothermal or solar, whatever. The fact of the matter is, as we move forward, we will be moving to different heat sources than just natural gas and propane. And how do we account for this in our system designs? Okay, so a little poll here. I think Max is going to pull up.
Yep,
What
I'll
is your
launch
method
this.
for selecting a boiler or heat pump size?
So the third answer, I'm going to read the whole thing because GoToWebinar wouldn't let me add that much text. So it's stand across the, so answer C is stand across the street and see how many fingers it takes to cover up the house. Each finger is worth 50,000 BTUs per hour. So that's, let us know if that's your sizing method of choice. And then I'll leave this open for another 10 seconds here. Jake, I think we've got a runaway favorite here. So let me close it.
I hope it's number 3.
So yeah, number 3. Number 3 is not performing that well, unfortunately. Let me
looking at this attendee list, I see a couple of you on here that I know have done that before. So
And so we had, with 81% of the vote, perform a heat loss calculation, which is music to our ears. And we probably have a biased audience. If you're taking the time to listen to Coffee with Caleffi right now, you're probably hopefully doing it the right way. But Jake's going to kind of go through some of the examples there. Second place, we had the use the BTU per hour per square foot number with 14%.
which is pretty standard, and in a lot of applications that works just fine. But really the big takeaway there, and I'd love to see 80% of people saying they do a heat loss, which I like Max said, I think we probably have a skewed audience because I highly doubt that 80% of the actual installer base does that, just based on some of the things we see out there, right? But the big thing here is that everything we work off of when we're designing the system requires us to know our load. If you look at the universal hydronic formula, which if you all do heat losses, I'm guessing most of you are familiar with, what is the big thing we see here? It's all based around deciphering what our VT load is. So the heat load decides everything. How much energy do we need to move? How much do we need to create? The best way to do that is with a heat loss calculation, which for those of you who don't do them or haven't seen, a heat loss calc is essentially a calculation that looks at a building and decides how much heat we will lose out of the building or we need to replace with our heating system, to keep it very simple. It's looking at a design day, which for ASHRAE, it's a 98% or a 2% design day. I think ICC is 97.5%. What that's saying is we design the system to be able to overcome the load or 98% of the historical low temp day. So it looks at all the temperatures recorded in an area, and then it says, okay, we want to overcome 98% of those. So it gets rid of the top two or the lowest 2% temperature wise. So that -20, then -25. Some areas you go that low. Here in Montana, we have areas that are a 10 or a 20 below design day. There are multiple methods to do this. You can manually calculate it. Manual J, I would say, is the most common heat loss method. If you look around at most jurisdictions, this is what they require. A lot of jurisdictions are requiring manual J calculations on new build, unless you live here in Montana, and then we don't have a single jurisdiction that requires it. So, we just do it to make sure we are doing the right thing. Okay, so knowing our loads allows us to size our heat sources. Obviously, we're sizing off of a BTU per hour load. Size our heat emitters, whether that's a radiant panel, baseboard, panel radiators, whatever. We can't size any of this if we don't know how much heat we're trying to output. It also allows us to establish our flow rates. If we're looking at our universal hydronic formula, we can flip this around to calculate a flow rate. GPM is equal to our BTUs per hour divided by 500 times the delta T. Obviously, that 500 is a constant. It assumes, I believe, 62-degree water at sea level. So it's not 100% accurate, but for what we're working with, it gets us close enough. Delta T is always a little variable. It's one of those things that is worth having a discussion about briefly. 20 degrees tends to be our industry standard delta T. Does that mean it's the right delta T? No, not always. As with many things in our industry, 20 degrees has become the standard because it makes the math easy. We're a bunch of dumb plumbers. Installers, dividing by 10,000 is simple, right? So 20 times 500 is 10,000. I can divide any number by 10,000 without too much effort. If I make that 30, dividing by 15,000 is a little more difficult. I'm not going to tell you exactly what is the right or wrong delta T. It's constantly shifting in the system. Designing around a 20 will get you where you need to go. A little bit higher delta T, so going to a 25 or a 30 allows you to use less flow rate to move the same amount of energy. This is definitely a good thing in many applications. The downside, especially with, say, radiant, is it creates a wider temperature variation across a radiant panel. Your average temperature drops. So we may need to run a little bit warmer water temp, which can offset any gains we had in efficiency by going to less flow. We also need to understand if we start looking at hydronic cooling is going to require a much tighter delta T down in that 10 or 5 degree temperature differential range than heating. So we can have a lot of variables as we move across systems. It also establishes our pipe sizing. So pipe sizing is based on the flow rate we're trying to put through the pipe. We'll talk a little later about making pipe sizing selections as we move forward. So once we've kind of established our flow, we can start looking our flow, our heat loss. We can start looking at designing a system. So this is an actual system that exists. When you look at this thing, what is the biggest issue you see with this boiler system? I think, Max, are we going to take suggestions in the comments?
Yep, if you want to add something to the chat. And I had a clarifying question too about the last slide. 500, that number is works well for water. If you were in Fairbanks or something like that and you're doing 50-50 mix of glycol, you're going to take that 500 number down and have a penalty there as well. So
Yeah,
I'll keep an eye on the.
What's the number? I think you'd go down to about 460, I believe, for
Yeah, I
30% glycol, something like that.
It's something in the mid 400s, I think.
Yeah.
For kind of the mixtures that we normally see. And we did a coffee with Caleffi about glycol last year, I think, too, that went into a little bit more of the detail there. I'll look that up while you're talking. So I've got an answer here. Oh, this one's another Delta T question. I'll keep an eye on the questions for this and interject if there's something that looks like it's worth mentioning. But if you want to go ahead and cover kind of how you'd assess the system, go for it.
Okay. So the big thing that kind of goes with where we're going here is to address that we have no hydraulic separation in this system at all. So every pump, especially the boiler pumps, if these boiler pumps run, we are pumping through this entire system and we're in series with every system circulator that is in the system. So you can see in some of these areas we have zone valves and zone pumps. And in most of these, those zone valves were added because there was ghost flow. Even when these pumps weren't running, our boiler pumps were pushing through everything. So anytime we have pumps in series, we're creating inefficiency. Pumps in series, the basics of looking at it would be that you would keep your flow rate the same with two pumps in series and your foot ahead capacity would double. In reality, it also increases your flow based on where you fall on a pump curve. So anytime we're pumping through another pump, we're increasing our pressure through that pump, but we're also increasing the effective flow rate. So we really don't want to do that. It can create some issues. We look at this also, we're missing some check valves and other things, but we don't have time to go into all the details. So like I said, all these circulators directly interact with each other. We end up with some ghost flow, over pumping, poor heat transfer. As we close down delta T's, we don't lose as much heat, right? So when we look at this, piping that allows all circulators to function independent of each other is known as hydraulic separation, which is a big goal when we're trying to simplify a system. How do we let each circulator do its own thing without interacting with every other circulator? So one of the concepts to get here is closely spaced T's. And we've gone through this in just about every hydronic training 1,000 times, but it's worth revisiting a little bit to understand the concept behind why it functions. So closely spaced T's work. For those of you who don't know, closely spaced T's are a piping configuration, like you see right here, where two T's coming off of a primary loop are very close to each other, hence the word closely spaced. Closely spaced T's function because there's very little pressure differential between the two branch takeoffs. So in a hydronic system or any closed loop system, water flows because, or system fluid flows because we're creating a pressure differential, right? Our circulators are not technically pumps, they're circulators, and they're just pressure differential machines. We create a higher pressure on the discharge, which creates a lower pressure on the suction side. And because it's a closed loop with nowhere to go, that pressure differential induces flow. Nature wants everything to be in equilibrium. So the fluid in your system will flow back and try to create equilibrium in that lower pressure area. When we look at closely spaced T's, if this second circulator is not running, our pressures on either side of the T's, because they're so close, are going to be the same. So there's no way to induce flow to come through these T's. So our fluid will flow right past those T's. If we spread those T's too far apart, now we will end up, because of friction loss, with a pressure differential. So if we have those T's far enough apart that we lose, say, 1 psi at the discharge or past the second T, what's going to happen? This area where we had 18 psi on our secondary now is going to try to equalize the pressure down here at this 17. And we're going to induce flow through this circuit when we didn't want to. The ideal thing is we keep these close enough, and we'll talk about the spacing in a second, that when we kick on our secondary circulator and create our own pressure differential, we will induce flow in this circuit, induce flow in this circuit, and they don't actually interact with each other or affect each other. This is an illustration of how we would create closely spaced T's. If you look at Hydronics 15, download it if you happen to have a copy. It really goes into the nuts and bolts, the formula of how we come up with these spaces. And this is very helpful if you're trying to nail your piping down exactly. There are some rules of thumb that work very well in what we do without having to do all the math, but some of us really don't like. So the rules we really want to pay attention to, center to center of your T's needs to be a maximum of 4 pipe diameters apart. And that's the diameter of the takeoff, right? So if this is 1.5 inch main and we're taking off with 1 inch piping, these two T's can be no more than 4 inches apart. If it's 1.5 inch piping, no more than 6 inches apart. Center to center. The absolute max that we run into is 12 inches. So even as we get into very large piping, where say with 6 inch pipe, the math would say you could be 24 inches apart, we still want to try to get that to 12 inches. Commercially gets a little different, but for our general purposes, we want to work with smaller pipe sizes. So if we keep them within 4 pipe diameters, we're going to keep that pressure differential to a minimum and should induce no flow. Another thing to understand is that our flow rates have to play with what's called conservation of flow. So if we have the circulator shut off, our primary circulator is running, and we're moving, say, 10 GPM, we will carry 10 GPM across these T's. So this pressure entering the T configuration or pressure, flow entering the T configuration and leaving the T configuration always have to equal each other. If we kick this circulator on and we have this circulator is also running at the same flow rate, 10 GPM, we will have 10 GPM coming across. All 10 will go up our secondary circuit, come back, and re-enter the primary loop. So everything is in equilibrium. So these two always have to be the same, and these two always have to be the same. Say we have a smaller circulator on our secondary. We will kick that on at, say, 5 GPM. 5 GPM will pull up out of the main, 5 GPM will come back. For our flow rate to be conserved across that primary, that means we'll have 5 bypass, right? So any flow that does not go up the secondary will bypass and continue through the primary loop. If we have a larger circulator, say we're doing 20 GPM, we'll have 20 GPM pull out of that loop. 10 GPM will actually have to bypass backwards at the top of this pipe. We used to have a clear piping configuration that would show this, and you can actually see the water moving along the top of the pipe to come backwards and fulfill this 20 GPM in the secondary, and we'll still have that 10 coming across. And this does do some funny temperature things as well, as you can imagine, which we'll talk about here. So this is another way of creating that hydraulic separation. So a hydraulic separator is another way to create the same thing. Hydraulic separator is a large tube with your 4 inlets and outlets, 2 inlets, 2 outlets. Essentially, it is creating a, thanks Max, this is also touched in Hydronics 15. It's creating a very low pressure zone in the middle. So as that flow drops into our big barrel, the velocity slows to almost zero, and the water then can move to wherever it's induced. As we look at this, and this is where we can introduce temperature to this equation, the equation we see down here from Hydronics 15 tells us exactly how to calculate the temperature differentials we're going to talk about. One thing to note, if you are building your own hydraulic separator, I recommend you just buy one from Caleffi. It's a little simpler. But if we do want to build our own, the rule of thumb is the barrel is 3 times the pipe diameter of the incoming. So if we have a 2-inch incoming pipe, our barrel is going to be a 6-inch barrel, etc. So as we induce flow through a hydraulic separator, if our flow rates are the same on the incoming and the outgoing, we'll call this a boiler side and a system side. All of that temperature will just go straight across with our flow rate. So if it's 10 GPM and 10 GPM, everything moves across, we carry full temperature. If we have a higher flow rate on the system side than the boiler side, we will actually pull return water from the system back and mix it with our outgoing water. This is the same thing that we would see with flow going backwards on a set of closely spaced tees. This is something to pay attention to because you will get a slightly lower outgoing water temperature than you would to your system than what the feeding boiler water temperature is. You can use this formula to calculate what temperature you need to have from the boiler to feed your system with what set point you want if you know you have a higher flow rate on this side. And then the opposite, if we have a higher boiler flow rate, we will pull hotter water back and return a higher water temperature to the boiler than we are bringing back from the system, which most of the time is neither good or bad. We just need to know that that's happening. This is actually, you'll see this happen quite often as variable speed circulators in modern hydronic systems slow down, and a lot of our boiler circulators are constant speed. So when we get only a small zone calling, our pump is, or our circulator has slowed down, we will start returning a higher water temperature back to the boiler than we are bringing back from our system. One thing to note, if you start seeing this, there are situations where our smallest zone is larger than the minimum turn down of a condensing modulating boiler. If we're bringing an artificially high return water temperature back, boilers modulate down as they see the delta T of their supply and return close down. So as the boiler reaches its set point and that delta T artificially is closing down, it can actually modulate itself down below the requirements of whatever the single zone out here calling is. So if you go to a system and the complaint is that I have one small zone that never can get up to temperature and everything looks okay functionally in that zone, pay attention to what your flow rates between the boiler and the system are when only that zone's calling. We could actually be modulating that boiler down below what the requirement of that zone is, and it's never feeding it quite enough heat to overcome that that load. So potentially we would want to adjust the bottom end of the boiler or use a variable speed pump on the boiler. So talking about boiler and system piping with hydraulic separation, this is probably 2 very common piping configurations you'll see from boiler manufacturers. I get this question all the time. Which one should I use or which one is correct? Does anybody have any input? Max, I don't think we did a poll here, but if anybody has any thoughts in the comments.
Yep, I'll just keep an eye on the comments as people type in here. I don't see any.
Let me know if one significantly overrides the other.
We've got a couple questions. We're going back to the Hydronics 15. But you can go ahead and cover it. I'll jump in if there's something else that people are still typing.
Yeah, let me know if there's anything else. And I'm moving kind of fast here. Once I get talking, I get moving. So we can definitely address any questions or comments towards the end. So end of the day, both of these are correct. Neither one really has a huge benefit over the other. We're creating our hydraulic separation and keeping our circulators separated in both of these. Most of it will come down to preference. Some boiler manufacturers have one preference or another based on their heat exchangers and flow rates they would like to see. So do pay attention to what your boiler manufacturer says. But end of the day, if you see either of these configurations, they will work just fine. Another concept to talk about with separating our flows is looking at, once we've created separation, utilizing what we would call short fat headers to feed variable zones or temperature circulators. Anytime, this could even be zone valves in reality, anytime we have a header where we have multiple things taking off, we want to look at oversizing this header to, again, back to this same concept, create minimal pressure differential between all of these T's. So we really would like to create this where there's almost no friction loss between the entry of the header and the end of your header. The general rule to do that would be to size that header to create 2 foot per second velocity in the header based on your flow rate, right? Generally speaking, you will size your system piping based on around 4 foot per second, usually less than 5. 5 foot per second velocity is where we start hearing water move in metallic piping. If we get to 5 foot per second, that's where you'll start hearing water velocity moving through a pipe, which we generally try to avoid in a residential system. If we get all the way up to 7 foot per second, that's where we start eroding metallic pipes, specifically copper. We definitely want to try to stay below that 7 foot per second mark. So this 4 foot per second tends to be where we design for. There's always a little wiggle room here, right? 1 inch, 4 foot per second is about 11 GPM, 1.25 inches is about 16, 1.5 inches can handle 23 to 25, 2 inch up to 40, etc. Like I said, there's definitely some wiggle room on either side. If we look at sizing headers at 2 foot per second, these numbers, for those of you who do design, are going to look a little crazy, right? Where, say, in this system, in this illustration, we used 1.5 inch hydraulic separator. We'll just say we had 18 or 19 GPM in this system with all these circulators running. So at 19 GPM, we could use 1.5 inch separator. It can absolutely handle that with no problem. However, 20 GPM or 19 GPM puts us all the way up to 2 inch copper for our headers, right? So we would use the smaller size separator, and we could get away with 1.5 inch piping on the boiler side and just transition to the 2 inch after the separator, or where we start building this header. We could actually have some piping before this and create the header a little later on down the line, depending on your configuration. The real key is we're creating this header before we start any takeoffs and continuing it full size all the way until we stop with our takeoffs. So we can maintain that minimal pressure differential across the board. It'll help us equalize our flow capacities and help these circulators not have an effect on each other, which is definitely ideal. The next thing to consider is our basis of pretty much all hydronic design at this point is pumping weight, right? So Dan Holohan, Holohan published a book in 1994, I believe, 31 years ago, that really popularized this notion. It's not, I don't think Dan actually invented it, right? But he definitely made it popular within our industry and spread the word of doing this. So the concept of pumping away is placing our air separator and expansion tank at the suction side of our circulator, system circulator, or circulators. This could be a header with multiple circulators, it doesn't matter. And also attaching our feed point. So either a glycol feeder, fill valve, however we want to fill our system. Ideally, I prefer feed tanks. If we're going to use a fill valve, that's perfectly fine. Shut it off after your system's been commissioned to avoid leak issues and flood issues in a home, right? We want to be pumping away from our air separation for a couple of reasons. Our air separator generally gets located on the suction side of these circulators because air comes out of solution at the lowest pressure and higher temperature point in your system. So the lowest pressure point of your system is on the suction side of a circulator. The highest temperature is generally right before your system circulator where our boilers are feeding in. Or if we didn't have primary, secondary, our boiler's just sitting over here feeding through this, right? So we are also placing this here. So we're pulling air out of our system at the highest temperature, lowest pressure point. Our circulator at this point is also putting its highest pressure out into your system. So we are taking entrained air at the highest pressure and putting it through our system and letting it come back to the lower pressure area instead of having the circulator down here pumping back at this, where we are putting our higher pressure through the boiler or through our system or through our piping rather than out into our system, where it can hopefully carry that entrained air through the system and back without it coming out of solution in your radiant floor or at the top level. Anybody who's ever worked with a cast iron radiator system or a large baseboard system knows it's not fun when that air comes out of solution on the third floor in the corner of a cast iron radiator that doesn't have a vent on it, right? So we want to try to keep that entrained air in solution all the way through our system. We also want to feed at the same location as our expansion tank because this is the point of no pressure change in the system. That means it is the only point in the system where our circulator will not affect the fill valve pressure or the glycol feed pressure. If we put our glycol feeder over here, it's going to see an artificially high pressure and not do its job. And if we put it way down here, it can still function, but it could see an artificially low pressure versus what the system's actually doing. We also want to make sure we're including purge points. This goes to our maintenance side. If we are filling this system, we want to be able to fill either from our feed tank, ideally not the feed tank, but from a feed line, or from a purge point, close this valve, feed through our system. We can allow our circulator to help push that through, pull back, and we can purge air out at this lowest point. So these are kind of the basic concepts that we can pull together to create a system that's functional without going overboard on getting too deep. So again, utilize these basic concepts to design simple yet effective hydronic systems. I couldn't tell you how many contractors I've talked to who go out and look at a system that's been installed or something they did or their guys did and come back and say, can we just get back to pumping away? What's the most basic thing we can do to get a system that does what we need? So hopefully that's where we're starting to approach, right? So if we look at this semi-complicated system where we have a high temp takeoff snow melt with a heat exchanger, mixing for our radiant system. This is carrying off to an indirect water heater over here. We've got all kinds of fun things tied in. We did tie in properly where we would like our expansion tank and our glycol feed to be. However, we put this way up top here, which height does matter. However, this is the least used part of the system. This is either makeup air or secondary forced air backup. where most of our flow rate is either going to go down through our heat exchanger or through our radiant system, and we never pass through our air eliminator. And our pressure can be changing up here with all of our circulators functioning down here. Um, so that wouldn't be ideal. How could we simplify the system using what we've talked about? To a point, there is no simplifying a massive 600, 800,000 BTU boiler system with snow melt and radiant and makeup air and everything else. But we could use some of these concepts to eliminate some issues we've had and to cut down on piping and potential issues, right? So we've used a hydraulic separator in line here. This now becomes our air elimination. I generally do not like to tie the glycol feeder in the expansion tank into the bottom of a hydraulic separator. Um, the reason for that is that a hydraulic separator acts not only as air elimination, it's also dirt and many times magnetic separation if we're using a set 4. So when everything shuts down and we've been eliminating dirt from the system, where does it gather in this? Right at the bottom, right? So if our expansion tank and feed unit are tied into the bottom of the separator, when the system settles down, what happens? That all drops right onto the top of the expansion tank. And then when pumps and everything kick back on, or system pressure drops and we start putting pressure back in with our expansion tank, we just push all that dirt and magnetite, whatever, back into the system. So if you want to use this port, what we need to do is drop essentially a dirt leg off the bottom of it. So do a takeoff from the bottom of the separator, keep a drain valve at the bottom, and tee off to go to your expansion tank in your feed system, be it a glycol feeder or a feed line. You also can just pull that off to the suction side of your system. So that simplified this piping configuration that we totally missed. Pretty simply, we built a larger header, so we did a short, fat header that eliminated all, in this system, this is actually all 2-inch pipe. So it eliminated about 30 to 40 foot of 2-inch pipe, and we used about 6 foot of 2.5-inch pipe to build a header that can eliminate a lot of this piping that's taking up a ton of space in this room. And also, a lot of 2-inch is way more expensive than a little bit of 2.5-inch. And then we do our takeoffs to all of our different circulators. We didn't change anything on the secondary side. We did put check valves in so that our flows are not interacting with each other. In this system, we tended to have return water from this heat exchanger with no check valves be pulled all the way back around here and be pulled through our mix valve. It was a fun one to troubleshoot. So this is one way to take these concepts and take a relatively complex system, which it still is, but simplify it a little bit where it's much easier to identify what's going on, and we are using a little bit less material as well. Here's another application that's maybe a little more common than a massive 2-3 boiler system that we deal with. So this is a single whatever size boiler. We have a higher temp. We'll call this a baseboard zone or area. A area of, say, gypcrete, which we're mixing down from a boiler temperature, and a small basement area, which we're using a mix valve. This is using injection mixing. There's absolutely nothing wrong with this piping configuration. It functions, it works. However, we could simplify this down to eliminate some piping and also eliminate 3 T configurations that you have to nail the sizing on, right? So especially if you have inexperienced installers working for you, you have an interesting space that you need to pipe this in. Getting closely spaced T's to the right sizing and configuration can be difficult. One thing to keep in mind with T's that I didn't touch on, the direction of the takeoffs does not matter. You could have 1 T pointing this direction, 1 T coming this direction. As long as they're in a line and spaced properly, there still will be no pressure differential. What we can't do is take one T around the other side of a 90, or change direction with a 90 or 45 in between T's. So sometimes a large piping configuration like this can be pretty difficult to pipe. So using those same concepts that we looked at on the last one, we could simplify this down a little bit. Short fat header, hydraulic separator. We could also use a single closely spaced T configuration here. Our high temp injection system and mix valve. So this simplifies and uses significantly less space and eliminates some tricky piping configurations. One thing to note here, we have
to clarify with that, or to ask you about, so you've got injection mixing on the second one and then a mixing valve on the third. I've heard people say that, well, the third one will have cooled down enough that even if it were low temperature radiant, you don't need a mixing strategy there. Do you want to talk about that a little bit as far as putting them in series and assuming the water temperature will be, 180 at the beginning of the line and 140 at the end of the line?
Sure, absolutely. And there is, some math to back that concept up. What that to a point will depend on is exactly which of these temperatures are calling, right? So assuming we have a modulating boiler that has multiple temperature capacity, so we can run this at 180, 140, or 120. If only this is calling, we would be able to run this at 120 and you don't need any mixing. However, if only our baseboard zone is calling and only this in-slab radiant is calling, we have no way of assuming that we would get this all the way down to 140 or 120 without a mixing device, right? If we put 140, or let's call it 180 through this first baseboard zone, and we're bringing it back at 160, a 20-degree delta, and none of our gypcrete is calling here, or this gypcrete is so satisfied that this mixing or injection pump is not running, this is just running on its own on a small zone, we'll still bring 160 back to the takeoff of this low temp radiant. So if the whole system was running, Max, you're correct. By the time we bring return temp here, it goes out here, brings a lower return temp back. In theory, with the whole system up and running at max load, we could do the math and come up with that design. However, in partial load situations, we're really not protecting that slab at all.
Yeah, perfect. Yeah.
Does that answer that, Max? Or?
Yep. Thanks for walking through that.
Because what we're seeing here is as we bring return water temperatures back in each of these T configurations, the supply temperature to each consecutive one is going to be lower if they're all running. In this situation, we don't have that effect. All three of them will get essentially the same water temperature from the boiler, which you could argue is a little less efficient in some manner. However, mixing tends to work way better if we have a fairly consistent incoming temperature and we know what we can plan on there. And again, we could run through water temperatures, and if only this low temp is running, it wouldn't be a big deal to pull only low temp across. And ideally, we're also running on outdoor reset here. So that's another concept, but that leads us to partially that question, Max, of how many water temperatures do we really need? Here's one system I ran into a while ago where we have a big primary loop and 1, 2, 3, 4, 5, 6, 7, 8 different mixing valves with their own zone pumps and their own zone valves, right? Which tells us a couple of different things if we really dig into this. This is what the system design looked like if we mapped it out. We had 2 boilers, a large circulator that carried through this whole loop, and then a takeoff for each zone. All of these zones are staple up radiant. So we really didn't require a bunch of different water temps. We can also see that these T's are nowhere near close enough together. So zone valves were added after the fact because we were getting ghost flow through each of these zones. Because the T configurations really didn't work with this large circulator here. But do we really need 8 different supply water temperatures? Depends. So generally speaking, our supply water temperatures are determined by the heat emitters that we're using, right? So if we're using baseboard, we base it on manufacturer rating. Baseboard has an X output at Y water temperature. Same with panel radiators, fan coil units, anything like that. They will be based, or we will utilize our water temperatures based on their ratings. Now with radiant panels, it's a little bit different. We don't get a rating from a manufacturer generally. Supply water temperatures are calculated and depend on the required floor surface temperature and the insulation value of your floor covering, right? How much heat we can get out of a slab or staple up configuration. If you are using something like LoopCAD to do your heat loss, when you tell it what your installation method is, put your tubing in, and do the heat loss, it'll actually calculate these temperatures for you at worst case scenario or design temperature. If you're just walking into a job, you can actually sit down and calculate what these temperatures would look like or for each panel or zone so that we can look at how many temperatures we would actually need. You use a chart similar to this one, thanks to Uponor. This is a chart that they've provided. We need to know our installation method. So in this situation, it's a 4-inch concrete slab. Our tubing's 12 inches on center. Our BTU per square foot load required. So we have to have that, again, that load requirement calculated before we do this. Our room set point here, so 65 degrees. Floor covering, R value. How thick is that carpet and pad, or how thick is your wood covering? Or we have a tendency, contractors up here tend to put a 3/4 inch piece of plywood over any gypcrete installation and floor covering on that. So we have another 3/4 inch of OSB that we need to get heat through before we can get to the surface. And then our desired delta T. So if we know some of this information, we can go to this chart. Let's say we have a 20 BTU an hour requirement and a R value of 1. So we would follow our 20 BTUs over to where we intersect with that R value of 1 for the flooring, which is probably a hardwood floor with maybe a sheathing underneath. We can drop that down. And if we're working with a 20-degree delta, we know we're going to need around 110-degree water temperature. If we're working with a 10-degree delta, we can get away with about 105 degrees. It's a lower water temperature because our average temperature in that panel, since we're moving the water through it faster, is going to be higher. You can see here with different types of installations where we hit different water temps. We need much lower water temps for a 4-inch concrete slab than we do with staple up with plates, right? It's an even bigger difference if we don't have plates. But if we look at that same 20 BTUs with an R value of 1 on our floor covering, we come down to somewhere north of 150 BT or 150 degree water temperature to get 20 BTUs an hour out of our slab, where we were at 110 before. That's a situation where we absolutely need 2 different water temperatures. One thing to consider when we're talking about different water temperatures is the floor surface temp. So this is another thing that needs to be calculated. Most floor coverings have a maximum floor surface temp. Most hardwood manufacturers want something below 80 degrees. Some will go to 85 degrees surface temp. You also, just for comfort purposes, don't want to go too far beyond that. So we can look at this chart that kind of gives us a lot of things. There's a lot going on here, but if we have 20 BTUs a square foot and we know we had an R or a floor covering value of 1, we can get away with 100 degree 100-degree supply water temp, and that'll equate to somewhere in this area of surface temperature. Now, if we did that same thing and had a 140-degree supply water temp, we're going to be in this 80, 79, 76-degree range, depending on our set point. So we want to try to keep our surface temps down, and you can see the differences as we work with much higher water temps and higher BTU outputs where we end up. Sorry, I can see I'm running out of time here, so I'm trying to get through this. I told you I was going to be too wordy. When do we need multiple water temperatures? Required temperatures, if we have areas that vary by more than 20 degrees. It's a somewhat arbitrary number, but generally speaking, if we're within a 20-degree requirement, it's going to be safe to use that higher number and depend on zoning to keep that lower requirement happy. If our higher temperature exceeds the maximum surface temp for flooring or an install method, we absolutely need to protect floors, construction, concrete slabs, etc., and keep temperatures below that. Concrete guys say 150 is the absolute max you want to put into a concrete slab. I personally would go significantly lower than that, but per the Concrete Association, 150 is the absolute max. And also areas with radically different heat loss characteristics. We don't want to put a super high temperature into an area that has very low heat loss. That's how we overshoot area temperatures. So in this situation, how many water temperatures did we really need? Zones are staple up with heat transfer plates. All the floor coverings are hard, either hardwood or ceramic. Each circulator and mixed valve are a single zone, right? How would we simplify this down? Turns out, end of the day, we really run all of them at the same temperature. So instead of having 8 mixed valves that can fail, 8 additional zone valves, if we wanted to stick with zone pumping, we could have simplified this down to a hydraulic separator rather than the more complicated boiler separation piping that we had, and run it all on a single temperature, and the system works just fine, rather than trying to dial in each zone to a very specific temperature. So again, keep it simple. Anytime we're looking at these, what's the simplest way that we can heat to the level we want without going overboard? It's a fine line. Again, the system that was installed worked just fine. We just had a lot of moving pieces and a lot of additional costs that maybe we didn't need. And that becomes service issues down the line. 2 minutes. And again, I'm probably going to go a little over. If anybody has meetings they need to get to, please jump off. Otherwise, I will get through this and we can answer some questions at the end. So, Max, I think we had a poll here. What do you guys see as the future of hydronic heating and cooling, as that may be?
This one, go ahead and just type your answer into the chat, since it's kind of an open format one. And then, yeah, I'll keep those. They may take a second to type in. I'll keep those to the end and we can read through them.
Perfect. So we can have a bunch of different answers. You know, some people will still want to see cast iron boilers make a comeback. Or in a lot of our markets, especially on the East Coast, it still is certainly a thing, right? Condensing gas, air to water heat pumps, hydrogen is more of a European thing than an American thing, but definitely is making a push. Any way we look at what the options are or what you would prefer to see, the future of hydronic systems are very likely going to be low temperature systems. As we move away, again, whatever your opinion is, we are moving away from fossil fuel burning. It's just the way it is. As we move into things like condensing boilers, where we can still burn gas, air to water heat pumps, and ground source heat pumps, and then even electric boilers, all of these operate with their highest efficiency at the lowest supply or return water temperature possible. Condensing boilers are most efficient with the lowest return water temperature. Air to water heat pumps have their highest efficiency at certain outdoor air temperatures, but always with the lowest supply water we can do. And ground source heat pumps are the same. The less it has to boost that water temperature, the more efficient they are and the less energy we use. So given that, as we look at especially new installs, but even retrofits, we should be considering lower temperature systems. Ooh, mix that up. So what does that mean? It means using heat emitters that require lower supply water temperatures and are compatible with all of our heat sources. So currently what we have as well as the next gen. This can mean something like radiant floors and ceilings, which can operate under 100 degrees. Some that operate at 70 or 80 degrees, supply water temperature up to 140 or 50, right? Radiant ceilings, you can run definitely higher or lower water temperatures. Radiant floors, they all kind of vary, but definitely can work in that lower temperature range. Panel radiators are an excellent option. You can run panel radiators again if you size them properly, anywhere from 80 degrees up to 140, 150, 160. These are a great option if we're trying to retrofit an existing house that has baseboard or cast iron radiators. And we want to try to future proof it and move to something lower temperature that will work with heat pumps or electric boilers. We can size panel radiators to fit almost any application or any space. Something like this can very easily replace a standing cast iron radiator. Some of these options actually look similar to baseboard, can fit in the same space as existing baseboard, however, can operate at a much lower water temperature than baseboard. And then another option are low temp fan coil units. These are excellent options if we're using heat pumps and we want to be able to do cooling with hydronics as well, right? So these are similar to really dumb it down. It's like a panel radiator with a small DC fan built into it that induces airflow across the heat exchanger coil. They come in many shapes and sizes, something on the wall that looks like this. You can also get them that are built into the floor, or you would call that a trough unit. Multiple manufacturers out there. In the air to water heat pump space, this is really probably the most common and future of where a lot of that's going to go. As far as being able to utilize a very low water temperature, this is actually my house. You can tell we have a very varied sports household, but I have panel radiators in my basement that are all oversized to run at the same temperature as my radiant heat system that's on the main floor of my house. So I only run a very basic boiler situation, a now defunct boiler with a hydraulic separator and just a single circulator that's feeding multiple zones of either panel radiators or radiant. So all of this runs at a single water temperature. I run an outdoor reset curve that starts about 75 degrees, and when we get to zero outside, maxes out at about 130 degrees, and never have any issues with the radiators or the radiant. So this is a very simplified, simple system that can fit multiple different heat emitter types and not involve a bunch of mixing. So a couple considerations to take into account, right? Heat pumps generally require or operate best with extended runtimes. Honestly, condensing boilers are at their most efficient at the lowest firing rate for the longest period of time. We want to consider in our designs thermal energy storage or buffer tanks to extend the runtimes. We can install buffer tanks now with standard boiler systems that would allow for a heat pump to be installed later on down the line with minimal piping changes. So buffer tank sizing is really covered in depth in Hydronic 17. I'm out of time here, so I'm going to get through this fairly quickly. Basic sizing for an on-off heat source, so a cast iron boiler, or a modulating heat source, which can be a heat pump or a condensing boiler. We want to know our minimum runtime. With an on-off source, it's our input rating or max input minus the smallest load. So that one little bathroom zone that takes 500 BTUs, we need to know what that is because we're trying to size a tank that can allow that to run while still inputting a much larger uh, load. And then our delta T times 500, right? The difference with the modulating heat source is we base this on the minimum input rating of that modulating heat source. So like 200,000 BTU condensing boiler with 10 to 1 turn down, we would use 20,000 BTUs here rather than 200,000 BTUs, which allows us to have a significantly smaller tank. Just a couple basic piping configurations with a 4-port tank. If we look at Hydronic 17, John Sigenthaler did an excellent job of providing options with various types of tanks. Not every buffer tank has to be a 4-port tank, right? We could have 2-port, 3-port. There are options in there. I recommend you take a look at that. But for a standard 4-port buffer tank, this is a pretty basic illustration of how we would fit that in. And if we moved to an air to water heat pump down the line, now all we're doing is adjusting piping from here over rather than having to add a buffer tank and try to pipe to it 10 years down the line or whatever that may look like. If you're in New York or Seattle, it's probably right now you need to be looking at that, right? If you're in Montana, we don't do a ton of air to water. A lot more ground source geo. This also, we want to be considering cooling. The future of hydronics with water, air to water or ground source heat pumps really is going to be trying to integrate heating and cooling, either with radiant or fan coils, however we do that. But to compete with the air side and to really try to grow our industry, we want to be able to offer both heating and cooling as temperatures rise, et cetera, right? As we look at that, utilizing items that can do cooling as well, we're designing our systems to be able to function with that is highly beneficial. Not going to go a ton into radiant cooling today. Obviously, we don't have time, but you want to look at low temp fan coil units, traditional chilled water fan coil units. I've seen chilled beam commercially, especially. I have seen it in some residences. It works very well. So cooling, some design considerations. We need lower delta T's. Cooling generally is going to operate at a 5 to 10 degree delta T where we run heating at 20 to 30, which means piping and pumping systems vary between the two. That's a control issue to take up, but understand that we may need larger piping and larger circulators to do cooling, and we're going to have to modulate those down for heating purposes. We also require pipe insulation and condensate management, right? If we're using these low temp fan coil units, they will condense in cooling mode. When we're installing them, we have to consider how we're going to get condensation away from the units so we're not flooding a building, right? It's going to be very similar to what we have to do with kind of standard mini splits, a small condensate pump, or in NewCon, working with the plumbing contractor to make sure we have somewhere to drain condensate nearby. And insulation so we're not condensing in walls, right? Awesome. I flew through the end there. So Max, thank you.
Yeah, no problem. Thank you for being the guest today. I think that my favorite example there is that seeing as many systems as you've seen, just like the one temperature with just adjusting the size of the panel radiators down in the basement and things like that just makes a lot of sense and is less to keep up with maintenance and all those things. So yeah, thanks for walking through that. We had a couple comments as you were going about the future of the heat sources with air source, CO2 heat pumps, air to water heat pumps. We had a solar thermal comment with a question about where can you get solar thermal stuff anymore. We used to offer a full solar thermal package and it worked really well in a scenario that PV didn't just like completely run away with the solar market. So I think that, fortunately for everybody, but maybe unfortunately for solar thermal, solar PV just got so much less expensive But I wouldn't sleep on solar thermal if you were going to use an enormous amount of hot water. So there have been some like laundromat projects or like a rec center or something like that, that if you're going to just, your alternative is a ton of propane to heat water for a pool or something like that, that's where solar thermal can be a good way to go. And the lift isn't as high as trying to get it up to 180 degrees or something as well. Let's see, I'm going through some of the other questions. There was a question we had talked right before the webinar about insulation. You mentioned it for the like chilled water piping, basically. Do you want to give that analogy that you're talking about with the difference between the insulation and the wall? I thought that was kind of applicable to pipe insulation as well.
Oh yeah. So we were talking about trying to decide when you add complexity to a system, right? Or it also functions for wall insulation, pipe insulation. If you look at how effective insulation in a wall is, the difference between no insulation and R19 insulation is massive. The curve just does this, right? You shoot up and it's a huge difference. Now the difference between R20 and R50, while the number looks bigger, the actual effectiveness shrinks significantly. It's the law of diminishing returns, right? Once we get to a certain point, the effectiveness, while better, still drops off. And it's the same thing with pipe insulation, right? No pipe insulation is the worst. A half inch of the cheapest thing you can get is 10 times better than nothing. And then you can get up to 1 inch of foam rubber, high-end insulation, which is definitely better. But understand that even the minimum of pipe insulation is way better than none. Is that kind of where we're looking, Max?
Yeah, that's what I was looking for there. And then I've got another one that is, I'll just read it out. What's your take on really old systems that are historic cast iron radiators, high temp, old steam converted to water? Go back in with the cast iron boiler because of the high temperatures, aren't as efficient with like a modulating boiler or something like that. What would be the way to assess that if you were in charge of the Bozeman City Hall or some old building like that, to figure out how to make it modern and keep as much of it as possible, or decide if it's going to work or not?
I think there's a lot of things that play into that equation, right? With cast iron radiators, or even just baseboard systems, you're not going to change anything out. As we look at higher temps, I still believe there is a place for cast iron boilers. From a cost and longevity perspective, especially. If the whole system is one zone and everything flows and everything's on, it's perfect. You're really not going to gain a whole lot from a condensing boiler. I think where you can gain from condensing boilers, even at high temp, is if the system is very zoned. So if we have loads fluctuating significantly, the modulation factor of modern condensing boilers is where you get your savings, even if it's not running lower temperatures, right? Because we're able to input much less gas as our load drops. Where with a cast iron boiler, you may have 1, 2, 3, 4 stages, but we don't actually modulate. Also, with the modulating boiler, we can run outdoor reset where, in Bozeman right now, it's somehow the middle of December and 50 degrees out. So do we need 180-degree water when it's 50 degrees outside to keep this building warm? Ideally, we would be able to turn that down way more, where maybe we can get into that higher efficiency rating of the condensing boiler in those shoulder seasons. That's also where you can look at something like an air to water heat pump to use for shoulder seasons. And then when our supply water temperatures start rising, it switches over to a hybrid, to a gas system. I really think a mix of air to water heat pumps and gas hybrid systems is probably the immediate future of our industry, because we don't have the capacity.
I think that's a great point. That I think if you have the space in an older building, leave the cast iron boiler just for that like coldest month of the year, or coldest, really it ends up being coldest 5 days of the year that you need that much heat. But I think that the counter to that is, like you're saying, that there's probably most of the shoulder seasons that those radiators don't need to be red hot. And then it's kind of a nice quality of life improvement that if the radiator isn't going from room temperature to 180-degree water where it's ticking and clicking and kind of the things that people that have lived in old buildings think have to be like that. If you just had 120 degrees for 60 minutes of an hour rolling through that, and it was just warm but not boiling hot, that's kind of nice. And that's something that with a good control strategy you could do without abandoning the cast iron or using it in a hybrid system like you're describing, which
I think what you find on cast iron is the vast majority of it's way oversized.
Yeah,
it just is. It was how things were installed 100 years ago, right? So most of them can handle a much lower water temperature than they've been getting for the last 90 years.
I forget what the period was during was it the Spanish flu that they were doing heat losses, assuming the windows were open. So yes. If you get into like a century-year-old building, that radiator is going to be great for a lower temperature system because it was designed assuming to get the what did they call that? Just like the stagnant air from making people sick, which they were onto something there. But you'd be in great shape with that. You could go to 140 degrees, just a ballpark number there, but you'd have to run the numbers. But yeah, you might luck out with that in a really old building.
Yeah, absolutely.
Well, I think that the rest of these questions are a little bit more specific that we'll get back to. I'm just seeing if we missed anything, but we were answering a bunch of them as we went through. So let's wrap it there. Thank you, Jake. Thanks for going through that. That was a great background for simplifying things, and keep up the good work up there. And we appreciate you taking the time to present today. We will be back in February. So we always take the month of January off because we're usually getting ready to go to the AHR show in Las Vegas. So we'll be there with the booth, and then we'll be back with John Siegenthaler in February. And we'll send that around as soon as we get all the details finalized. So thanks again, Jake, and we'll talk to everyone soon.
Thanks, everyone.